Hello, friends. Welcome to the third session of our series on overcurrent and earth fault relaying. In the first two sessions, we have already discussed about the concept of overcurrent and earth fault protection. We have discussed in detail about the instantaneous, time delayed, and IDMT characteristic. In the first two sessions, we have also discussed about the coordination of non-directional overcurrent relay using IDMT characteristics. Uh, we have considered some example in which we have uh, seen how to calculate time dial setting or time multiplier settings and how to set the minimum pickup like this. So in this session, basically we are going to discuss about the directional overcurrent protection, what are the need for directional overcurrent protections, and we will discuss about 2 to 3 different types of cases uh, and how to coordinate those directional overcurrent protection in those cases that will be discussed in this session. So in the first two sessions, we have discussed about the four topics. In this session, we will discuss about the need for the directional overcurrent protection. Remember, we are not going to discuss about the uh, concepts of how to determine the direction. That we will discuss somewhat later, maybe after 1 or 2 sessions, when we discuss about the polarizing quantities, RCA, RO, etc. So now, without wasting any time, let us start with today's session. And these are the things that we have already discussed in our initial two sessions. So if you have any doubts in these things, then you can just comment in the comment box. And if I know the answer, definitely I will try to answer those questions. So now we have discussed these things in the last session. So today's session will be on directional overcurrent protection. So basically, why directional overcurrent protection is required. So consider a simple example in which we have two source A and source B. Basically, the directional overcurrent protection is required whenever uh, current can flow in both directions through a relay location. So if suppose this is one of the relay, and if from this relay current can flow in both directions like this and this, then we have to decide in which direction this relay should trip. This relay should trip in this direction, or this relay should trip in this direction, or this relay should trip in both the directions. That we have to decide. So the important thing here is if the current can flow in both directions through a relay location, then we have to have the directional overcurrent protection. Now consider this very simple example. And now if you consider this example, suppose we have a fault here. Before that, if you see, there are some numbers like 0.159, 1.3, 1.7, and 2.1. So this is basically done by using a simple coordination example that we have already considered in the last session. And this coordination is using definite time grading, where we have the fastest operating relay closer to the load end if we not consider this source. So fastest operating relay is nearer to the load side, and all other relays are zero point 0.4 second, 0.4 second, zero point 0.4 second coordination time interval, that is. So now consider a fault which is at this location. So for this fault, this and this breaker will trip and the fault will be isolated. So this is good as far as we consider for this particular fault. Now suppose the fault is at this location. So for the fault at this location, what happens? Now for this fault at this location, fault current will flow from this source like this, and also the fault current will flow from this source like this. So this relay will see the fault current. This relay will also see all these relays will see the fault current. And now, very simple thing is, if this current, this fault current, suppose whatever this fault current is, if this is more than the set values, then this relay will also operate and there will be widespread disturbances. So now if this source was not there, then what happens? If this source was not there, actually the fault current will flow only from this source to the fault, and so this relay will not see any fault current, and these will not trip, and only this feeder will trip. Definitely after a very large time delay of 2.1 for this particular case, but there will be only the tripping of one feeder, and all these feeders will continue in service. But for a radial line or a single source, if this trips, then there will be no power in these sides. But now, since we already have source from both ends, so this and this, and if now all these feeders are tripping, so unnecessarily we are causing a widespread disturbance, because now only if these trips, we can have a source of power to these buses through this source. So now what should we do? In this case, we can use directional overcurrent relay in such a way that these relays should operate only on the basis of the directions of current flows. That means these relays should only operate for a given direction of current and should not operate for a second direction. Uh, some people might ask here that the current is going to change in every 10 millisecond for a 50 hertz system. So yes, current is definitely going to change in every 10 millisecond, and we are not talking about how to determine this direction, because the direction determination uh, in an AC system depends upon some reference quantities known as polarization quantity, and we will see it in the upcoming sessions how to determine the direction. Right now, we are only saying that whenever the current flow in one particular direction at a time of fault, then only relay should operate. It should not operate for the direct any other directions which is not as per our requirement. Now consider this case again. This is the same case. So in this case, now if we are using this type of grading, we have seen it is not okay. It will lead to widespread disturbance. Then how should we coordinate? So now if you see here, we have some directions like this relay should operate for this particular direction, this relay should operate for this particular direction, this relay should operate for this particular direction, like this. And now if these relays are operating like this, so definitely after some time, whenever this time elapses, this will isolate the fault. But first of all, how to determine this time and how to determine this direction? So let us consider this same example. So we have suppose I just number it like source 1, source 2, and I'll also number it like relay R1, R2, R3, R4, R5, and R6, and maybe these buses as A, B, C, D, and then we will see how to determine this current, how to determine this direction. So what we will do, first we will consider only one source, and we will do all the coordination by removing this source. Then we will consider the second source and remove the first source and do the coordination, and then we will merge both. So just consider the first case in which we are now considering source 1 only, and we will consider these buses. So how many buses we have? We have 1, 2, 3, 4 bus. So I will just consider 4 bus, and now I'll just also rename these as A, B, C, D, and suppose these are our uh, city brake air protection system, completely everything with relay. So now this is R6, this is R1, R2, R3, R4, and R5. Now, if you see, I have just removed this second source from here. So now just consider the case like if we have a fault on this bus bar. So in the case of a fault on this bus bar, what happens? This source S1 will feed the fault current like this. So now, which relay is closer to fault in this particular case? So now, if suppose this relay R5 operates and trips its associated breaker, this breaker, then definitely this feeder will be out and fault will be isolated. So the first relay, which is very closer to fault, is R5, and I'm assuming the minimum time of operation for this relay as 0.1 second. Now, if R5 fails to operate, then the next relay comes as R3, and R3 should operate after of time of zero point 0.4 from this R5. This zero point 0.4 is basically coordination time interval, and the concept of coordination time interval I've already discussed in the earlier session, like why this coordination time interval is zero point 0.4 or zero point 0.3 or for that matter anything. So this we have already discussed. I'm not going to discuss it again, but if you see this time of operation for R3 will come as zero point 0.5, and if R3 fails to operate, then R1 should operate, and R1 time of operation should be zero point 0.5 plus zero point 0.4, that is 0.9 second. Now, if you see what should be the current direction for this relay, if you see for R5, the direction is like this. So R5 is like this, R3 again, this is like this, and R1 is like this. So this is for the first case. Now just consider the reverse case in which we are assuming that the fault, now we have removed source 1 first, and then we will see. So we have now only source 2, and these are our relays. So again we will do exactly same thing. First we just number it like R1, R2, R3, R4, R5, 6. And now consider the fault is at the remote bus. So now if for this fault, what happens, this source S2 will feed the fault current like this, and the relay which is very nearer to the fault is now R2 and with this current direction. So R2 we should operate with a time delay, minimum time delay, same as above as zero point 0.1 second. Now, if R2 fails to operate, then R4 should operate and should trip this circuit breaker here, and it will now cause a disturbance of this and this feeder. So in this case, the R4 time of operation should be zero point 0.1 plus zero point 0.4, that is 0.5 second. And if R4 fails to operate, then R6 should operate, and for R6, the time of operation will be zero point 0.5 plus zero point 0.4, that is 0.9 second. So now, if we just club both, that is with source 1 and with source 2. So if you want to club now, then what happens, this relay 0.9 second, R2 it will be 0.1 second with direction this, R4 0.5 second from here with this direction, R6 0.9. Now, if you see for the relay which are closer to the source, these relays should be non-directional. Why? So, for example, suppose if you have a fault here or if you have a fault here, then for this fault also from this side the current will flow. Similarly, for a source like here, if the fault is here, the current will flow from both the direction. That is what you can see from here also. The current can flow for any relay which is closer to the source, the current can flow from the both direction, and it is a general practice that all relay which are closer to source should be non-directional. So now if you see here, this first one is 0.9, then 0.15519. So first you see this 0.9, 0.15519. First and last relays are non-directional because it is nearer to source. So these two relays nearer to source are non-directional. Then your second relay, the current direction is from right to left. So this current direction is from right to left. Third relay, the current direction is from left to right with time of operation 0.5. So left to right, time of operation 0.5. The next relay, time of operation 0.5, current direction from right to left. So 0.5, right to left. The next relay, 0.1, current direction is from left to right. So 0.1, left to right. So in this way, we have just coordinated these directional overcurrent relay with uh, each relay having a set current direction for operation and a set time delay. So now if suppose we have a fault here, for this fault what should happen? This fault will be fed from both sources, this source and this source both will feed the fault. Now for this fault, this relay will pick up, this relay will pick up, because it is non-directional. Uh, this relay will not pick up because this relay will see the fault in the reverse direction, because for this relay the operating direction is from right to left in my screen, but the current is flowing from left to right. So this relay will not pick up. This relay, the current direction is this for our relay, assumed current direction for operation, and the at the time of fault, the current is flowing from left to right. So this relay will pick up. This relay will also pick up because it will see the current in the same direction as per its setting. This relay not pick up because its operating direction is from left to right, but current is flowing from right to left, and this relay will also pick up. So now if you see what happens, first of all, which are the relays which are picking up? So relay, both non-directional relay at the source end are picking up, and then the relay which is closer to the faults are picking up. And in this particular case, after 0.5 seconds, this and this relay will operate and this will isolate the fault. If the fault current still persists, for example, suppose after 0.5 seconds, this relay has operated. So this relay will operate and it will trip this breaker. But if this trip this breaker, the fault current cannot flow from this side. But this relay will still see the fault from this side. So now what happens? Since this relay has already operated and cannot clear the fault, so after another 0.4 seconds, this relay will trip, issue a trip command. It will trip this breaker. Uh, yes, it will cause widespread disturbance because now this and this will be tripped. Actually, this and this strip means this source is basically isolated when this strip. So from this side now the fault current will not flow and this fault is isolated, and at this particular time your this particular portion will remain healthy and will feed the power from the second source. So in this way, if we are using directional control, we can control the power flow during fault. We can control which relay should operate. We can control what should be the time of operation. Now, this is a very simple example, but consider now a case of a little bit complicated case in which although now we have only one source, but it is connected in ring. So this is like a ring connected system with a single source. In the next one two slide, we will consider a ring connected system with multiple source. So before going into the multiple source, we should first understand the concept of ring connected system with single source. So in this case also, if you see for any fault, suppose a fault is here, we can have the flow of current from this side and flow of current from this side. That means now we have a current flow at any particular point. We can have a current flow for load or current flow during fault in uh, two direction, and that's why now we need a directional control. Again, if you see, there are two different numbers, 51 and 67, both are overcurrent. This is time delayed overcurrent protection, time delayed overcurrent protection, and this is basically non-directional. This 67 is directional overcurrent protection. So if you now see here, there are many relays which are directional and the two relays which are nearer to source that we have already discussed in the last slide. The two relays which are nearer to source are non-directional. Now, if we have these types of system, if we have these kinds of ring connected system, then every utility have their own setting philosophy and they should establish that philosophy, that how to coordinate, what to use. We are only discussing the generalized things. We will only discuss which relays would be non-directional, which relay should be directional, and what should be the time of operation for that particular relay. But that particular time of operation is only using definite time. In a real case, we have to consider the maximum fault level, then we have to calculate the IDMT curve TMS and time of operation, and then we have to coordinate like that, which we have already discussed in our second session. So now, if we want to coordinate this particular case, then what to do? Again, if you see there are some numbers written over here. So I will just explain to you how to determine this time of operation, how to determine that in which direction this relay should operate, in which direction this relay should operate, that we will now see. So if we have this kind of system, this kind of ring connected system, then first of all, in case of coordination, what we have to do, we have to consider that this point is open and the current can flow only from this end. And then second case, we have to consider that this point is open and the current can flow like this. And we have to coordinate all the relays by considering one point at a time, and then we will merge like we have done for our previous case. So consider this case. I will explain. Suppose this is our source and we have one, two, three, four buses. So I will just draw it. So this is my source and this is my one bus bar. Then this is second bus bar, third, and this is fourth, and this is like this. We have some relay here. Now I have intentionally I have not connected it because I will discuss first how to what I am trying to achieve using this. So I will also use the same nomenclature which is used in the last slide, that is A, B dash B, C dash C, D dash D dash C, and A dash. So A, B dash B, C dash C, D dash D, E dash E, and A dash. Now, like I have already discussed, so if we have to grade or if we have to coordinate these relay, first we consider that this point at A is open and point at A dash is closed. Now consider one fault which is here. For this fault, as I have already discussed, the current will flow like this. Now, for this particular case, when the current is flowing like this, if the relay B dash operates, it should isolate the fault. So the minimum time of operation should be for the relay B dash, and we are considering this time as 0.1. Now, again, this is same thing. The minimum time of operation I am considering for all our example as 0.1. In coordination time interval, I am considering as 0.4 second. So now if B dash fails to clear the fault, then which relay comes next? The next relay comes is C dash. So if C dash operates, yes, it will trip this and these two feeders, but the fault will be isolated and remaining feeders will remain in service. So C dash, the time of operation should be 0.1 plus the coordination time interval of 0.4, that is 0.5 second. If C dash doesn't operate, then or C dash fails to clear the fault, then D dash should clear the fault, and this time of operation will be 0.5 plus 0.4, that is 0.9 second. If D dash doesn't clear the fault, then E dash should operate and it should clear the fault after 1.3 because 0.9 plus 0.4 is 1.3. If E dash fails to clear the fault, then finally A dash will trip and it should clear the fault. I have already discussed in the last slide or last to last slide that the relay which is closer to source should be non-directional. So A dash should be non-directional with time of operation 1.7 second. For B dash, the current direction is this. For C dash also the current direction is this. For D dash, the current direction will be this. E dash, the current direction is this. Now we will consider the second condition in which now we will consider that this point is open and this point is closed. So I will just draw it again. So now this point I have considered closed. I will draw the bus B, bus C, bus D, E, and then I will close. So this is D dash D, this is E dash E, this is B dash B, C dash C, A, and A dash. So now this is case 1, this is case 2. So now we have considered that the ring is open at this point and ring is closed at this point. Before in the case 1 we have assumed that ring is open at A and closed at A dash. Now we have just assumed the reverse condition and we are assuming one fault here. For this particular fault, the fault current will flow like this. So now for this particular fault, which relay is very nearer to the fault? So relay E is nearer to fault, and if relay E operates, it should trip its associated breaker here, and then the fault will be isolated. So for relay E, the time of operation will be the minimum time of operation, that is 0.1 second. Now if relay E fails to trip, then the next relay, that is D relay, should operate. When this operates, it will trip this breaker, and this whole section will be isolated, and other section will remain healthy and remain in service. So relay D, the time of operation should be 0.1 plus coordination time interval of 0.4. So this will be 0.5 second. If relay D fails to clear the fault, then C should operate and it should isolate the fault. And for C, the time of operation will be 0.5 plus 0.4, that is 0.9 second. If C fails to clear the fault, then B should operate and its time of operation will be 0.9 plus 0.4, that is 1.3 second. And if B also fails to clear the fault, then finally A should trip and it will isolate the whole system. And this time will be 1.7 second. There are two things that you can see. Whenever any relay away from the faults are operating, basically the backup relay. For example, this E relay is basically the primary relay for this fault. So the primary relay operates, it will isolate the faults uh, very quickly. But if primary relay fails to operate, then the backup relay on the other bus will operate. But when this operates, there are two things. First, the fault will be isolated, delayed, and second thing, it will cause a widespread disturbance. So this thing again we have already discussed in our initial sessions. So I'm not going to discuss it again. Now, if you see for this E relay, what should be the operating current direction? So this is my fault direction. So E relay should operate like this. For D, the fault direction is like this. So for this, it should be the current direction. For C, this should be the direction of operation. For B, this should be the direction of operation. For A, I have already described that this is nearer to source, so this would be non-directional. So now if we club both, if we club case 1 and case 2, A will be non-directional with time of operation 1.7. B is in this direction with 0.1. This is B dash. B in this direction with time of operation 1.3. C dash this direction 0.5. C this direction 0.9. D dash this direction, D again this direction with time of operation 0.5 second, and E is this direction with 0.1 second. So this is what is mentioned here. This non-directional 1.7, 1.7. Then if you see here 0.1, 1.3, I have also 0.1, 1.3, the current direction here. C dash C 0.5, 0.9. So if you see here 0.5, 0.9. D dash D 0.9, 0.5, 0.9, 0.5. This is 1.3, 0.1. So now consider any case, consider any particular fault. So now consider a fault is here. For this particular fault, what should be my current direction? So this source, it will be like this, and at the same time, the fault will also flow like this. So now for this relay, it is a non-directional relay. So this relay will pick up this relay because its assumed current direction is from right to left, but the current is flowing in this direction. So this will not pick up. Again, this relay current is flowing like this, and this is the assumed current direction. So this will pick up. If you come here, this relay, the current direction is this. Setting is also this. So this will pick up. This relay not pick up because the current direction is this, but the setting is in this direction. For this relay, now the current direction is this. This direction of setting direction is also this. So this will pick up. This not pick up. This relay will pick up. This relay not pick up, and this will pick up. So now what happens when there is a fault? So for this particular fault, within 0.5, because this is now the lowest operating time. If you see it within 0.5, C dash will operate, and once C dash will operate, the fault current cannot flow. So automatically D dash, E dash, and A dash will reset. Uh, from this, current will continue to feed till 1.3 second, and after 1.3 second, B will operate and it will isolate the fault. So when this operates, finally only these two sections will be tripped and other section will remain in service. So this source will continue to feed up to point C, that is up to this relay, and or up to this bus. Similarly, from this side, it will continue to feed up to this bus. So this is two very good example to understand the requirement of directional relay and how to coordinate the directional relay. Remember again, we are explaining this concept of directional relay on the basis of CT only to understand the concept. We will discuss in detail how to determine these directions using the concept of polarization quantity, MTA, RCA, ROC in the upcoming one or two sessions. Then it will be very, very clear. Right now, the concept is that we should trip only those sections in which the current direction is in the same direction as we have assumed during our setting. So now consider another example. In this example, now we have a ring system, but that ring system is now connected with multiple sources. So now again, this is exactly the same example as last example, with the only addition that now we have additional source B. So for this particular case, now this is again a very unique type of challenge that comes now, and this is basically a real world challenge when we are going to coordinate using overcurrent relay. These types of challenges will come. So in this case, what happens now? Consider a fault at location F1. For this fault, relay B dash should operate and A dash should not operate. That means ADAS will operate only when all this other backup relay will fail, then ADAS will operate. That means for this fault F1, B dash should operate before A dash. Now consider the fault at F2. For this particular fault, what happens now? That A dash should operate before B dash. So this is now big challenge that when the fault location moves from one point to another, then our requirement changes. So there are multiple challenges with overcurrent. One of the challenge when fault location moves from one point to another, then we have to trip. Our requirements of tripping the feeder changes. Second challenge is with the presence of different types of source, the magnitude of fault current will change. If the magnitude of fault current will change, definitely your time of operation is going to change. That means the coordination will definitely be affected. So these things we have already discussed in detail in our very first session on transmission line protection, that why overcurrent protection is not used and why distance protection is being used in transmission line protections. So that's why I'm not going in detail. So if we have this kind of situation in which we have a ring main type system but with two or more sources, then for coordination we have two options. The first option, and that is very simple option, is in case of any fault, suppose we have two sources, that is source S1 and source S2. So first thing is we have to see which source is important for us, whether source A is important for us or whether source B is important for us. So now suppose this source is important and this source is least important. In between these two, that is, this is important, this is not important. So whenever there is a fault, the least important or not so important source must be tripped instantaneously, and then the other relays should be coordinated by considering only the important source. So this is one option. Second option is we can use pilot method, that is carrier based method, in which we can consider a common source bus bar, and this bus A and bus B, we can consider a common source bus bar, and then we can use pilot protection, and using that pilot protection we can just trip one particular section. We will discuss in detail about this pilot based overcurrent protection in our upcoming sessions. Uh, this session we will keep only up to this point, because in the upcoming sessions we will discuss about this pilot based overcurrent protection, and then we will discuss about the coordination challenges for parallel lines, how to do coordination in parallel line with single source, in parallel line with multiple source. So these things we will discuss in the upcoming slides, basically in upcoming sessions. So I hope the concepts which are discussed in this session is clear to all of you. In case you have any doubt, you can ask your doubt in the comment section. I will try to answer those doubts if I know the answer. Even if I doesn't know the answer, I will ask from someone and I will try to answer those questions. Uh, we will keep this session only up to this point, and we will meet again shortly. Till that time, thank you and goodbye.